Up to this point, when we would talk about a derivative, we were talking about a numerical value. So if you were to say, for example, I have the function f of x equaling x cubed minus x, and you wanted to know what is the derivative of this at, say, 2, then what we would do is we would let a become a 2. A was, the value at which you wanted the derivative to be found. And the definition of derivative said that f prime of a was equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. So the procedure was, and we'll walk through this one for practice, might not be a bad idea. The procedure would be to, first of all, at least me personally, I go ahead and find out what's f of a. And in this case, f of a is f of 2. And f of 2 would be a 2 cubed, which is an 8, minus a 2, which is a 6. And then also off to the side, f of a plus h would be an f of a 2 plus h, which is 2 plus h cubed minus a 2 plus h. All right, and so going ahead and bring this over into the problem. This is the limit as h approaches 0 of a 2 plus h cubed minus the quantity 2 plus h minus the 6, which was the f of a all over h. Now at that point, there's some algebra to be done. It's the limit as h approaches 0. And now I've got to cube a 2 plus h. Now, there's a couple of ways to approach this. You could take the 2 plus h, write it out 3 times, and cube it out. What you're going to end up with is a 2 cubed plus 3 times 2 squared times h to the first plus 3 times 2 times an h squared plus an h cubed minus the 2 minus the h minus the 6, because I'm going to distribute the minus sign here all over h. So again, doing some arithmetic, 2 cubed is an 8, 2 squared is a 4 times 3 is a 12, h to the first power. That's a 6 h squared plus an h cubed. All right, minus the 2, minus the h, minus the 6, all still over h. Then a little bit of combining like terms. 8 minus 2 is 6, minus 6 means that is gone. And a 12h minus h, then 11h, plus a 6h squared plus an h cubed all over h. Now notice that an h will factor out here as a GCF. This is the limit as h approaches 0. And a h times an 11 plus a 6h plus an h squared all over h. And then finally, what we've been gunning for is for that h to cancel. So this is the limit. H approaches 0 of an 11 plus a 6h plus an h squared. And when you plug in the 0 for h, out of this, you get an 11. All right. So again, all of that just to find that numerical value. and it's just an 11. So what that would mean is that this function has a slope of an 11 at 2. Now, as you can see, that's a lot of work to go through. That's a lot of time. That's a lot of effort. So if you were to ask me, all right, well then what's its slope at 3? What's its slope at 4? What is its slope at 5.5? I've got to repeat that process again and again and again and again. And to me, that's just too much work. I'm not going to keep doing that repeatedly. So what we want to be able to do is come up with the derivative written in the form of a function. The original item that we want to differentiate is a function, and we want its derivative to be 1 as well. One function, a function of x, where I can plug in any number I want and know the derivative at any x value that I desire. All right, so let's take this same function, and we're going to say we want to know its derivative not at 2, but at any number x, any x value. All right, so therefore, at that moment, the definition of derivative is going to be rewritten. And here's the new version of it. We're going to say that f prime of x, not f prime of a, not f prime at a specified numerical value a, but f prime at any number x is going to be equal to the limit as h approaches 0 of f of x plus h, not a plus h, but f of x plus h minus f of x all over h. So I'll be using the same formula, same procedure, just doing it at an arbitrary number x instead of at a specific number a. And for f of x, then x cubed minus x, this is going to be the limit as h approaches 0 of x plus h cubed, because that's the f of x plus h, minus x cubed minus x, because that's the f of x, all over, okay, oh, hold on, I forgot one, missed a piece of the function, apologize. F of x plus h has another x plus h there, almost ran off and forgot that piece. All right, so here we see f of x plus h. Let me box it in just for a good visual here. Right, this is your f of x plus h because x plus h has been put in here. X plus h has been put in there. All right, minus, now here comes the f of x. F of x is the x cubed minus x. Now it's in both places. Almost lost that first piece. All right, so here's your x plus h in the f function. Here's the x in the f function. And again, it's all over an h. So, time for the algebra. Cubing this gives x cubed plus 3x squared h plus 3x h squared plus h cubed. Minus an x, minus an h, that comes from here. Minus x cubed plus x, which comes from distributing the x there, all sitting on top of h. Lots of cleaning to do. Let's see what all is going to happen here. Let's see. Oh, and that was not a square. There's no square. It's an x cubed. Now be careful and copy these numbers down correctly. So what's going to happen? X cubed is going to cancel x cubed real quickly there. 3x squared h. There are no other x squared h's. So that's taken care of. Plus a 3xh squared. There are no others. Plus an h cubed. There are no others. Minus x plus an x, that cancels. And minus an h. There. Finally, once you copy everything down, right there it is. Again here, the h factors out. There's the h down there. H's cancel. Now, for h, I'm going to plug in a 0. 3x squared is still there. This zeroes out, this zeroes out, and there's a minus 1. So what we find is that f prime of x is a 3x squared minus 1. That means if I wanted to know, which is a question I've already answered, what is the derivative at 2? It's 3 times a 2 squared minus 1, which is a 12 minus 1, which is the 11 that we got. And what's the derivative at 3? 3 times a 3 squared minus 1, which is a 26. What's the derivative at 0? So 3 times a 0 squared minus 1, which is a negative 1. I can find the derivative anywhere where it exists. Anywhere where it's defined, I can find the derivative. All right? So I say anywhere it exists. Well, where would it exist? Well, this is your definition of the derivative up here. And anywhere this limit exists, the derivative is going to exist. So what might cause that limit to not exist? Well, again, remember, this is an overall limit. And for an overall limit to exist, there has to be a left-hand limit, there has to be a right-hand limit, they have to be equal. All those criteria still have to be met. So let's look at some reasons. Let's look at some things that might cause a limit to not exist. And let's take a graphics approach for starters. For example, what if I was looking at this function? That's just an absolute value function that's been relocated. It's been moved from the origin right and up. Well, let's say it ended up at 3, 2. Well, the absolute value function is basically just two linears joined at this point. The line on the right-hand side has a slope of 1. The line on the left-hand side has a slope of negative 1. That means at any point here, if you take the derivative here, here, there, or there, it's going to tell you your slope is 1. If you take the derivative over here, over here, over here, over here, the slope's going to be negative 1. So what if you were to ask, what's the derivative right here? At that point, well, the limit from the left is going to be saying negative 1. The limit to the right is going to be saying positive 1. So if your f of x is absolute value of x minus 3 plus 2, which is what that function is, that's the absolute value function of right 3 and up 2, then f prime of x does not exist at an x value of 3 because the left-hand limit doesn't equal the right-hand limit. So what you're going to find is, as far as what does it take for a derivative to not exist, a corner point, which is what this is commonly called. If the function forms a sharp point, again called a corner, you're not going to have a derivative at that location. On the other hand, if you look at this function, where you have a discontinuity, commonly called, this one's commonly called a jump discontinuity. All right, the slope, as you see coming in from the left, is going to again be different from the slope coming in from the right. So a discontinuity of this nature would again cause your derivative to not exist. So at this x value, that derivative doesn't exist. It would exist everywhere else if you had a nice smooth curve. But at that point, it's not going to exist. And there are occasions it is possible for a function to go practically vertical at a particular value, and a vertical tangent would cause the derivative to not exist, right? So there are situations where the derivative will simply not exist. Now you'll notice, for example, this function is continuous. This function is continuous. We talked about a discontinuity here, but I have two examples here of functions that don't have derivatives at particular locations that are continuous functions. So therefore, if a function is continuous, we do not know whether the derivative exists or not. So continuous implies nothing when it comes to the derivative. All right, but on the other hand, since that limit has to exist for the derivative to exist, we do know that if f is differentiable, then it is continuous. So differentiability will always imply continuity, but continuous doesn't tell us anything about differentiable. It only works one way. That is a one-way street. All right, now, what does the derivative do? If you're looking at the derivative, you're looking at its function, what would that tell us about the original function? Well, if we look, this is something, for instance, I am not a great artist. This is something we need to look at in the book. Let's see what function differentiability tells us about the function, what the function tells us about the derivative graphically. And from a graphical perspective, I wanted to specifically look at, I found that problem. Here we go, number 39. I want to take a look at number 39 in particular. So we can talk about, again, what does one say about the other. All right. If you look and you're trying to figure out what does a function tell about its derivative, graphically speaking, what does the derivative, what does one say about the other? First of all, we know that whenever a function goes from increasing to decreasing, it has to pass through zero. All right. So if we look, for example, on number 39 at graph B, notice the graph B went from increasing to decreasing over here, just left of the y-axis, just left of the origin. That means that if the derivative of B is here, it has to equal zero. And if you therefore come straight down to the x-axis, you see C hits zero directly underneath that P. Therefore, C is the derivative of B. Also notice that wherever A, looks like A went from increasing to decreasing in here. So A went from a positive slope to a negative slope. So A has to have passed through a zero slope. So therefore, if we look from this point where it looks like it went from increasing to decreasing straight down, we see B. So in this graph, the derivative of A is B, and the derivative of B is C. Other things that tell us that is that here we see from this tip of A up to this point, A is increasing. Therefore, A's slope has to be positive. And notice that B is above the x-axis. Here, A starts decreasing. So A's slope must be negative. Therefore, that's why B is below the x-axis for those same values. All right, now we can tell that C's derivative is not here. C's derivative is not displayed here because here C went from decreasing to increasing. Its derivative went from negative to positive. So if c's derivative was here, there would have to be something intersecting the x-axis directly above that point, which is not the case. So figuring out where a function is increasing, therefore its derivative must be positive. Figuring out where it's decreasing, therefore its derivative must be negative. And figuring out where its derivative has to be 0 helps you to identify which function is the derivative of which. Now, something you're seeing here, there's a notation, hopefully you're noticing here, is they have an f, that means the original function. They have an f prime here, which means derivative. You're seeing an f double prime. And you may be thinking, well, that's new. I haven't seen that before. What would that mean? Well, we can take derivatives repeatedly. You can take the derivative of a derivative of a derivative. You can take it as many times as is needed. And here are some of the notations that go with that. If you have an original function and you take its derivative, you call that f prime. If you take the derivative of the derivative, and that is f double prime. So to put some definitions to this is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now this next derivative, again, how do we define it? Well, f double prime is the limit as h approaches 0 of f of prime of x plus h minus f prime of x all over h. So you take the derivative you had before and you put it back into the derivative formula again, and you have the second derivative. You can take a third derivative, and that's just the limit as h approaches 0 of f double prime of x plus h minus f double prime of x all over h. You can take a fourth derivative. And notice the notation. It looks like an exponent, but with parentheses around it. This prime notation only gets used for the first 3 derivatives, and then you switch to that other notation. This is the limit as h approaches 0 of f triple prime of x plus h minus f triple prime of x all over h. And you may be wondering, is it possible to go straight from a function to its fourth derivative or straight from a function to its third? Do I have to pass through all of these to get the one I need? Yes, unfortunately, you do. There is no shortcut formula that will jump you from a function to its fourth derivative or to its third. You have to go one derivative at a time. All right, this is one notation for it. There are others. If you look at f prime, that can be denoted by dy dx. That is one form of a notation for the derivative. This says derivative of y with respect to x. Therefore, f double prime is the derivative with respect to x of that original dy dx. All right. And that can be written as second derivative of y with respect to x, just like that. So this means you took the derivative twice of y, and it was with respect to x twice, both times. So therefore, your third derivative is the derivative with respect to x of the second derivative, which is the third derivative of y with respect to x. And again, this is saying differentiate 3 times, differentiate y, and do it with respect to x all 3 times. And again, this notation can be continued indefinitely. And again, you will have occasion, if you take both semesters of calculus or more, you will have occasion to take first, second, third derivatives and more and beyond. All right. So what are they used for? Why would I want to take multiple derivatives? Well, there are plenty of engineering and physics examples. All right. So for example, if you had a function which was a position function relevant to time, they often will denote those with an S. For whatever reason, S means position. So S of t is a function, again, that can represent position. Well, if you say, well, at what rate is your position changing instantaneously, that would just be S prime of t. S prime of t is rate of change of position. Well, we have another name for that, and that's a little bit messy. We have a name for rate of change of position. Rate of change of position is called velocity. So the rate at which your position is changing is called your velocity. If you take the second derivative of position, that's the first derivative of velocity, and that's called acceleration. So there is an application of your first derivative and your second derivative. If you were to take the third derivative of position, which would be the second derivative of velocity, which would be the first derivative of acceleration, that's called jerk. And you have to actually, I do believe, study a decent amount of physics to really get into jerk. But jerk's what breaks things in an engine, for example. The position of the moving parts in your engine don't cause damage. Velocity of moving parts in your engine don't cause damage. Acceleration of the moving parts in your engine it's not going to be what causes damage and causes you to throw a piston rod. But if your acceleration changes rapidly, creating jerk, then that's what can break things in an engine. All right? So jerk is a physics concept, and we will not really look much at jerk in here, but acceleration, velocity, position, these are all things that we will look at in the form of application problems.